Okay, let's continue with the last talk of the day before the lightning talks. Fabian Hopper will talk about heat, and we'll go massive parallel. All yours.
Thank you very much for this nice introduction. I will talk about the Helmholtz Analytics Toolkit. Let me just start with the question, what is heat and what can I do with it? Heat stands for the Helmholtz Analytics Toolkit, and it's a free and open source Python library for memory distributed high performance data analysis and machine learning on CPU and GPU clusters. So memory distributed, for those who are not so much familiar with that, that means really you have separate machines. So for example, the nodes of a compute cluster, and that's a complete different setting to, for example, the shared memory parallelism you have inside your workstation. And the topic is performance, is data analysis and machine learning, and we have a focus both on CPU and GPU clusters. The target group are scientists and engineers without an extensive background in HPC that still have to tackle data-intensive problems that go beyond the capabilities of a shared memory system, say a workstation, and there are more and more scientists of this kind nowadays, since the amount of data available is steadily growing. Why is it called Helmholtz Analytics Toolkit, you may ask? The reason is that it's a joint project of DLR, so the German Aerospace Center, Forschungszentrum Jülich, and KIT, Karlsruhe Institute for Technology, and these three institutions are members within the Helmholtz Association, and since this originates from a joint project within this association, it was called Helmholtz Analytics Toolkit, and you can also see there are several people from each institution involved. And not to forget, we have also some external open source contributors. For example, those of the Google Summer of Code of last year, and also some student workers that are not listed explicitly here. So a brief overview, how does it work? The idea is that as the basic data structure, we need some kind of replacement for a NumPy array, so an n-dimensional array, and this has to be distributed, memory distributed. So you can see, for example, if you just look at such an array, you can split this along one of its dimensions, so either along dimension 0, dimension 1, dimension 2, and distribute the chunks on different machines. So in this example, we have 3 machines. And the idea is to use PyTorch as the local compute engine. So that means this distributed array, we call that DND array, consists of PyTorch arrays on each process. So the advantage of that is, since we built on PyTorch, we can make use of these highly optimized routines that are there for the local arrays. So linear algebra, the NumPy-like interface, multi-threading on CPU, and which is particularly nice, we also inherit the vendor-independent GPU support. So once you use PyTorch, you can do that on NVIDIA or AMD. That's actually not a problem. And to glue these local arrays on each machine together to a global object, one requires some kind of communication. So these machines have to communicate, and there we use MPI. So MPI, I think, is the most standard way of let computers communicate, at least in the HPC setting. And we use MPI for Pi, which is just a library in Python that implements this MPI. And of course, our target is also to keep as close as possible to the NumPy API to make it easier for the user. And now what can you do with that? So we have these distributed arrays, but we have also a bit more than just these arrays. For example, we have some already implemented parallel I/O, so in particularly to HDF5, which is a format that is very common in high-performance computing. We have standard array creation and manipulation routines, quite similar to NumPy. We have a sparse, a basic sparse array class that originates from a GSOC contribution. We have basic statistics like min, max, mean, percentile, variance. So that's trivial on each process to make this clear, but globally on a large array that is distributed among several machines, this requires communication. And we have some linear algebra and are already extending that. And there are some basic machine learning routines. Here we try to extend step by step towards what could be interesting for our users. And finally, there's also some kind of possibility to implement data parallel neural networks. There's this so-called DASO algorithm. There's also a paper on that, and this has been implemented in HEAT. So you may ask, why another library for distributed array computing and machine learning in Python? So let's look at more or less a hopefully quite complete overview over this ecosystem and what makes HEAT interesting here. So the first selling point, of course, is that HEAT does this memory distributed computation. So you can use it in a multi-node setting, and in particular, you can do multi-node computations that are not embarrassingly parallel. Embarrassingly parallel would be tasks where you just do exactly the same to each data set on each node. That's embarrassingly parallel, but for example, if you do matrix multiplication or PCA, that's not embarrassingly parallel. The next point is you can do hardware acceleration. That's quite standard, I guess, in data analytics today, but in this multi-node setting, it's not always standard. Very important, we think, is that to have a simple NumPy or scikit-learn-like API such that a researcher who is used to use NumPy or scikit-learn for his workflow can adapt this with minimal changes to bring it onto a supercomputer. The next thing I already mentioned, since we built on PyTorch, we can make use of this vendor or platform independence of PyTorch. So, for example, if PyTorch supports an accelerator like a GPU, that's in principle also possible for HEAT. And also we do not require a very specialized software. So some of the packages I mentioned there require, for example, Chapel or PyComs, and more difficult software are optimized towards the GPU of a special vendor only. That's not our focus. Also, PyTorch ensures a high amount of interoperability. I think that's important. And finally, yeah, heat is quite general purpose. So you can do this distributed array manipulation, such as creation of arrays, adding, subtracting, dividing, min-max, and so on. You can do distributed linear algebra. So far we have implemented that. And yeah, machine learning on the level of scikit-learn. So far we have implemented that. And finally, via this DASO, you can also do basic data parallel neural networks. And maybe the most important thing is there are actually of these libraries there are only two ones that are also developed by scientists, Borium and Dislib. Borium is not maintained anymore, as I guess, because there's no commit since 3 years, and Dislib is really quite different. And I think it's important to have such a kind of library that is really hosted and developed by the scientific community and not by companies or other types of organizations. Yeah, in particular, for example, we as scientists are also interested if a user asks, can you implement something for us, then we would be interested in that, and maybe also a joint publication. And that's much easier to approach us than, for example, somebody of these well-known libraries. Yeah, let me give you a bit more details. So why this memory distributed setting? So the answer is quite easy, just avoid memory becoming a bottleneck. Let me show you a use case. You try to analyze 80,000 images, RGB images. You may ask, where come they from? That's from the DLR Institute for Aerodynamics. They do high-speed camera videos of rocket combustion tests, and yeah, then basically 8 seconds are just 80,000 images, and here was the task to perform anomaly detection, yeah, just to analyze this time series of images. And yeah, if you reshape that into a matrix, you get a matrix of roughly 200 gigabyte of size. And yeah, if you, for example, want to do DMD of that, then you need a PCA. So here I show you an example of a truncated PCA with truncation rank 1000. But actually what I show you also applies to different techniques, for example, clustering or just a matrix multiplication of such a data set. The important thing is to observe these tasks are not data parallel. So you can't say, okay, let's process this time series in chunks of 10,000 images and just do something with 10,000 images and do that in parallel. That's not possible because you have to keep in mind the whole data set if you do clustering. Or at least you need to do something more advanced than just doing the same on each data chunk. Yeah, that's what I said. Embarrassingly, parallel batch processing is not possible here. And that's why memory becomes easily a hard limit, and that's really something that should be kept in mind. Memory is usually a hard limit. Yeah, if a computation takes longer by a factor of 2, then maybe that's more expensive, and maybe you have to apply to get more time on your supercomputer, but in essence it's not a problem if it takes 2 days instead of 1 day. If the memory is over, yeah, then that's really a hard limit, so you can't change that easily. So let me show an experiment here. So it's about truncated PCA with truncation rank 1000. And yeah, so you can see in purple, that's the size of the array as a HDF5 file. And in green as a green cross, and in yellow you can see the memory consumption of scikit-learn truncated SVD. And the dotted line actually is the RAM limit of a standard compute node at the DLR cluster. And you can already see, in order to do the PCA with scikit-learn on a single node, you already need to switch to a special compute node, a big mem node, is it called, with 1 terabyte of RAM. And if you want to perform the computation in NumPy without truncation in advance, you see that even just 40% of the columns require almost 1 terabyte of RAM for the computation. And now, if we repeat that with heat, the truncated SVD, then you can see we can distribute the computation to more and more nodes, and that means the maximum RAM consumption on each node scales down, and we can easily do that also on the medium-size compute nodes. Yeah, so let me continue this. So yeah, what does strong scaling mean? Strong scaling means you fix your problem you want to solve, so in that case doing the PCA, and then you increase your computational resources, and of course you hope that the computing time decreases in the same way as you increase your computational resources. And yeah, what can you see? So as a reference, in green I have the scikit-learn truncated SVD. So actually we have to watch out. So it's not the same algorithm, so it's not really comparable here, but you can still see the scaling behavior. And what you can also see is you have many possibilities to tune the performance, because as I already said, yeah, so that's for different truncation ranks. Yeah, as I said, yeah, we inherit the hybrid parallelism from PyTorch. So actually, we only inherit the OpenMP, so the shared memory parallelism from PyTorch, and put on top of that the distributed memory parallelism with MPI. But that means you can tune the performance by yeah, choosing multi-threading in each MPI process. Yeah, and also nowadays I think the usage of GPUs is quite standard, and you see you can achieve very high speed ups when using GPUs. But again, this makes memory distribution very important, because you know a compute node, a CPU node with 1 terabyte, that's actually not a problem if you have enough money. You will never find a GPU with 1 terabyte, at least not at the moment. So I think the current maximum of the NVIDIA is 80 gigabytes, so you run out of memory quite fast. And then you have to distribute in this memory distributed setting. And let me just mention that. So heat has been used on Intel and AMD CPUs so far. On NVIDIA GPUs in our CI, we also have a runner with AMD GPUs. Unfortunately, we don't have an AMD GPU cluster to test it really. And one of our developers has a Apple notebook, and she's using that for development. So let's say there's some kind of experimental Apple support as well. But of course, this is not so important for a HPC library just because there is no Apple GPU cluster. Yeah, let me now say something about weak scaling. Weak scaling means basically what happens if you double the size of your problem and at the same time you double your computational resources. So if you do that, you hopefully end up with the same computing time. And yeah, so I did this experiment here for some basic task like loading from files, stacking data, applying a standard scaler, k-means, lasso, and truncated SVD. And you can see, except for the k-means, which is a bit not so optimal, you have quite good scaling behavior here. And the data set I used here is not the DLR rocket combustion data. That's now a particle physics data set, but actually the tests I perform with them do not matter at all for this data set. It's just to have some data set here. Yeah, let me briefly show benefits of the simple API. Let's assume you have such a NumPy scikit-learn code. So you load your data, you create this clustering object for k-means, you fit, and you print the cluster centers. If you want to do that in Heat, it's really roughly the same. The load is a little bit different just because you should not load txt files on a supercomputer. You load a HDF5 file. And the difference is now you specify just split equal to 1. That means you split your array along the dimension number 1. And then you can just go on as before with the same API as scikit-learn. So by standard, data is loaded on CPU. You can also make that explicitly. And yeah, doing the same thing on GPU is very easy. You just say, okay, load it on GPU, so that's very similar to PyTorch, and actually it's almost no additional effort to use GPUs here. And also, important, parallelization does not enter your script explicitly, except for this, which dimension you want to split, you don't have to do more. Yeah? So you don't need to specify the chunking of the data anymore. And also, it's easy to run that on HPC systems. You just use the usual Slurm type commands, and I think Slurm is very common on HPC system, at least in the scientific community. Let me briefly show you a comparison to Dask. With a short disclaimer, this has to be run by me, and I'm rather a Heat expert, but a Dask non-expert, so maybe the Dask part is not tuned optimal. And I want also to stress that Dask can actually do much, much more than Heat. And what we see here is that, of course, we have optimized Heat to do those tasks that it can do, yeah, for many things much faster than Dask, as it looks like, at least on a CPU. The problem was indeed I could not get a Dask to run on GPU because that interferes very in a very problematic way with the MPI installed on our cluster. And you will find more of these benchmarks also in the Heat paper. So if you go onto the web page, you can see that. Yeah, let me skip the two other comparisons with Dask and just go to the final slide, something on future development and challenges. So the first thing I want to mention is these software engineering tasks, like keeping and increasing software quality. That means, for example, in particular in the HPC setting, we do continuous benchmarking of the runtime and hopefully soon also memory consumption and energy consumption. Here the keyword would be green HPC. Yeah, so how does continuous benchmarking of runtime look like? So we have, for example, on our GitHub pages, you can see such diagrams for some routines. We measure the runtime for very small examples after each commit, and then you can see, for example, when we discovered an error in the the reshape function, then the runtime improved significantly. So that's quite interesting to watch that. Yeah, and of course, it's a challenge to keep and extend interoperability with the evolving ecosystem. So, for example, you have to watch out a bit whether PyTorch does some essential changes or not, and also whether interoperability is required with other libraries. Also important is to extend functionality. So as I said, we have basic linear algebra and we have some of the scikit-learn machine learning tasks, but of course not all of them. So the plan is of course to extend functionality as users want to use it. So a current project is, for example, to implement at least some basic support of something that is similar to X-array. The reason is that the Earth observation community uses X-array very much, and we have some connections to them through the DLR. And also the implementation of SVD and dynamic mode decomposition is going on. Here we have a contact to the ESA. And another idea is pre-processing module, FFT, or maybe if you want to suggest something, you can of course create an issue. And finally, community interaction. That means I think it's like for almost every library, you can always improve your documentation. That should be done. And finally, we want to support our users. As I already said, joint publications, for example, are always nice to have. And so to make this clear here, if you want to use Heat for your research, we would be glad to help you, so you don't have to contribute something to the code. We also just assist you in using it. And finally, feel free to try it out, also to suggest something, or if you want to contribute, and that's the link to GitHub. Thank you very much for your attention.
Thank you very much. Still very cool for Heat here. Any questions? There's one here, there's one there.
Nice thing. I also from Jülich, but not on the supercomputing side. So my question is about, so there's this Helmholtz Center and there are a lot of supercomputers there. Is Heat there pre-installed, or is this something the scientist has to do?
So actually you can install Heat by pip install. What you should make sure in advance is that you have some kind of MPI module loaded. Then you can install MPI for Pi just also with pip install and Torch as well. If you want to use GPUs, then you of course need to load the CUDA module, and to get optimal performance you need to manage to ask the sysadmins to install MPI-aware CUDA. So the problem is you probably will not find out if it does work, because you really would have to run benchmarks to find out whether some copying to the CPU is done in between. But in essence, usually it should suffice to have the modules loaded, the standard ones, and to use pip install in a virtual environment. But we also are in contact with colleagues of mine who write spec module specification, so then it's maybe easier to do that. But I'm not an expert in this spec package manager.
Thanks. More questions?
You said, hi, thanks for the talk. You said you had some initial sparse support, and I was wondering if you could talk a bit about like how much for sparse.
That's very basic. So we have this class implemented and operations that are and don't require too much communication. So that's very basic, but it's let's say, a starting point from which somebody could go on who wants to do that. So that was, so actually, this was roughly the size of one GSOC project to implement a, I guess, sparse CSR or something like that class here, and then so for example, adding two of these objects is straightforward. Also multiplying with a number, but of course matrix multiplication would require some additional work here. Yeah, so it's a very basic sparse module.
Okay, thank you very much. I think the time is over. Next is Lichen Source, but giving a big round of applause for this heated talk here.
Thanks.
So,